morning. I'm Tommaso Guffanti, postdoctoral scholar in the Stanford Space Rendezvous Lab, and today I'm going to present about the autonomous guidance, navigation, and control of the VISORS formation flying mission. VISORS is a multi-institutional project involving many universities around the US and also NASA Goddard. And specifically, many universities are responsible for different subsystems of the space mission, and specifically the Space Rendezvous Lab at Stanford is responsible for the guidance, navigation, and control subsystem. So the high-level scientific goal of VISORS is to verify hypothesis of solar coronal heating by performing imaging of the solar corona with unprecedented resolution, specific at the 0.15 arcsecond limit, and no existing coronal imager has reached this measurement threshold. The challenging aspect is that we want to achieve this unprecedented science by using a miniaturized distributed satellite mission in which the optical payload, so the detector and the optic, is distributed over two 6U CubeSats. Specifically, the detector lies on the detector spacecraft, which is on the right in this image, and the optics, which has been designed at the NASA Goddard Space Flight Center, it lies in the photon sieves that lies in the optical spacecraft, which is in the center in this image. And the two spacecraft have to align to the target region of the sun in order to perform imaging with a focal length of 40 meters. And this high focal length, which is achieved by distributing the optical payload, will allow for unprecedented high contrast imaging at the 0.1 arcsecond resolution. In general, other missions, obviously in the past, and as you can imagine, in order to achieve this kind of alignment, we need autonomous guidance, navigation, and control. Autonomous guidance, navigation, and control on miniaturized multi-satellite platform is not new to this mission. There has been other technology demonstration mission where try to achieve autonomous GNC. And here I give an overview of three of them, for example. One is the Prisma mission in 2010, which performed autonomous for a GNC using real-time navigation with differential GPS, which achieved accuracy around 5 centimeters and 1 millimeter, 5 centimeter in relative position, 1 millimeter a second in relative velocity, and used analytical impulsive control solution for relative motion control with an accuracy at the metal level. Then we have the CanX mission, which was a technology demonstration mission from Canada, if I'm not wrong, that also used differential GPS, achieving relative navigation accuracy of around 10 centimeters. And finally, there was the more recent CPOD mission, which technology demonstrate a fusion of different metrology from differential GPS to range and bearing angles measurements in order to perform autonomous guidance, navigation, and control for different purposes, so reconfiguration, maintenance. But as a matter of fact, the CPOD mission was unable to accomplish the rendezvous phase and just reached a closest approach of 1 kilometer. In the VISORS mission, instead, we aim to achieve some kind of really unique alignment requirements. Specifically, in order to perform the imaging we mentioned, we want to align the two spacecraft inertially with substantially having them aligned within a box which has an accuracy of centimeter level. So 15 millimeter on the longitudinal direction towards the target region of the sun, and 18 millimeter in the lateral direction. Moreover, we have also a requirement for imaging stability. We have also a requirement on the relative lateral velocity, which has to be on the sub-millimeter second level accuracy. So incredibly tight requirements that obviously have to be achieved with autonomous GNC, but cannot be achieved deterministically, given the fact that our navigation will, as you will see, will lie more or less will have an accuracy which more or less will be equivalent to this kind of accuracies in terms of control. So we will need to achieve this kind of alignment we will achieve this kind of alignment performances just probabilistically, and in particular, we aim for at least one successful observation over 10 attempts for having a 99% probability of getting at least one good observation after 20 attempts. In addition to alignment requirements, as you can clearly imagine, since we're working with 6U CubeSats, which will formation fly in close proximity, we have some very strict and relevant safety requirements. And the safety requirements, which are obviously from like collision avoidance perspective, are driven by also the nature of the miniaturized bus by themselves. In particular, we have subsystems which are going to be technology demonstrated from the very first time in orbit. And these are actually multiple and involve, for example, the very, let's say, fundamental subsystem, like the propulsion subsystem, crosslink subsystem. Therefore, we need to be robust to failures, at least partials, of this subsystem in different phases of the mission. And to do so, we need to employ a kind of a fault tolerance safety engine, which, as you will see, is going to be based upon passive safety in orbit. So the capability of maintaining a level of safe separation over a certain horizon, even in the case of sudden loss of control capabilities by any of the two CubeSats. Moreover, we are going to use the role of the CubeSats. So we're going to have one active and one passive CubeSat at each instant of time. And by switching the role, we can kind of mitigate specific contingencies that may affect just one of the two agents. And in addition, we're going to complement also this kind of fault tolerance and role switching with reactive escape. So at any time, so we're going to check in real time for safe separation, and if safe separation is going to be violated with a certain specific threshold on the uncertainty of this propagation, we're going to trigger reactive escapes, which are meant for separating the formation, which then will be reacquired to a nominal configuration. Thirdly, the third kind of requirements we have in this mission, I'm going very long, I already know, but whatever. The third requirement I have in this mission is a bus, kind of like a system requirements driven by the bus. In particular, we obviously have different subsystems which are going to impose requirements on GNC, and vice versa. Also, GNC is going to impose specific requirements on other subsystems. Here I mentioned just three of them, for example, which is we need, in order for having high accurate navigation, different GPS-based navigation, we're going to need to have some specific zenith pointing requirement of the GPS antenna for being surely to track commonly visible GPS satellites. But then, for example, the propulsion subsystem is going to impose a constraint on GNC and specifically on the control block of GNC of the type of maneuver discretization, the type of a maneuver that can be kind of actually implemented. Specifically, any maneuver in this mission needs to be kind of quantized into 2 mm/second bits separated by a minimum separation of 46 seconds that will allow the cold gas propulsion system to refill the plenum fully after each maneuver execution. The third one is related to the fact that in order to achieve high accurate alignment of the scientific instruments, obviously we need to kind of bound the uncertainty on the knowledge of the internal components of the spacecraft that have to be aligned. So we know that the dynamics is referred to the center of mass, but then we acquire measurements with respect to the phase center of the GPS antenna, and we need to align the scientific instruments. So there are three different elements which are located within the spacecraft, and the position of each element is affected by this own uncertainty. And ultimately, we will need to, we're going to estimate on board the vectors which connect center of mass to phase center that will allow us to have a good estimate then and a good alignment of the relative position within the two scientific instruments, given the dynamics model, which obviously acts with respect to the center of mass of the spacecraft. As you can imagine, this mission requires a pretty sophisticated concept of operation, which is characterized by autonomous and manual modes. Specifically, in order to perform downlink, safe downlink of data to the ground, the spacecraft will spend the majority of time in a standby mode relative orbital configuration, which is kind of like separated around 200 meters separation, and will allow to perform a downlink and get input from the ground in order to start a science campaign. When a trigger to a science campaign is sent from the ground, everything starts being autonomous substantially. And so the satellites then move to transfer autonomously to like a science configuration when now the separation go down to from 40 down to even 20 meters for performing alignment at 40 meters separation with the target region of the sun. And then when for example, 10 observations are performed, the spacecraft will autonomously transfer back to standby mode. If any contingency, and for example, if a violation of safe separation is detected at any time, autonomy, the multi-satellite system is capable of reacting and entering an escape mode, which allows to separate the spacecraft separation at any time in this multimodal concept of operation, and lead the spacecraft to a manual mode where it's going to receive ground commands and go back to the original standby mode. You can imagine both the absolute orbit design and the relative orbit designs of each of these modes is very relevant. And specifically for scientific observations, we will need to perform alignment in the tangential normal plane to minimize lateral relative acceleration during observations. And these requirements of performing observation in tangential normal plane, coupled with the requirement of being passively safe during science operations, substantially imposes a constraints on the beta angle of the absolute orbit we are launched in. And this ultimately, since we are going to be launched in a sun-sync orbit, this ultimately imposes a constraint on the local time of a standing node of the sun-sync orbit. And particularly on the plot on the bottom, we are showing substantially the expected launch window and the associated like separation in radial normal, radial tangential, and 3D that we expect having in the nominal science relative orbital configuration. That, for example, for the 10 a.m. case is depicted above. And as you can see, for this L10 value is passively safe actually, both in RN, RT, and obviously then in 3D as a consequence. So diving into the GNC architecture by more into the details. So the GNC library lives on the host software app on the bus onboard computer. And substantially the GNC library exchange data with multiple subsystems, including the attitude determination control subsystem, the GPS receivers, so metrology like sensors such as the GPS receiver and the laser rangefinders, with intersatellite link, propulsion, and also with the host software app by itself, which contains the higher level FDIR of the formation, and also with obviously ground rest of the ground through ground commands. Within the GNC, we have a data interface which allows like IOs and exchange of data with outside, and then we have mainly 4 blocks, which are a navigation block, a control block, a collision detection block, which is here called safety, and then also GNC full detection, identification, and recovery block. Within these blocks, we substantially have a specific suite of algorithms, which ultimately allows us to achieve the required, essentially the mission requirements from an alignment and safety perspective, and also like complying with obviously the bus requirements. So we're gonna, as mentioned, perform a differential GPS navigation with integer ambiguity resolution on board, which allows us, for example, with respect to missions such as Prisma, to go down to sub-centimeter relative position navigation accuracy, which is particularly key for like the type of alignment we aim to achieve. Moreover, we're going to have a suite of impulsive control algorithms, which are both analytical, so closed form impulsive control algorithms, but also optimization based, so that solve on board in real time a variety of convex programs, from second order cone to quadratic programs. And all these algorithms substantially run in different phases of the mission in a model predictive control fashion. And specifically, for example, we are going to employ closed form control, so closed form impulsive control solution during standby, mode station keeping, and transfer, where we're going to switch to more like an optimization-based control type of approach during the tight control in science orbit tracking, which allows us to go down to substantially to provide an available range of control accuracies over varying horizons from meter level down to centimeter level on horizons which goes from multiple orbits to a fraction of an orbit approaching observations. And finally, looking at the safety part, we're gonna, as I said, enforce from a concept operation or design perspective, passive safety throughout all the mission, but we will also allow for checking online for different kinds of passive safety, both like radial normal and 3D, which will allows us to be flexible, for example, in case in which we're going to be launched in like non-optimal sun-sync orbits with like L10, which is not exactly in the range we desire. And also we have a reactive option, which is triggered triggered by collision detection upon passive safety violation. Diving more into the algorithms by themselves, differential GPS navigation is performed by means of algorithm suite which has been developed in the Space Rendezvous Lab, which is digital, which allows us to perform integer ambiguity resolution in real time on board. Specifically, the measurement model is depicted in this slide and represents the double difference carrier phase range model in between the receiver of the two satellites, A and B, with respect to commonly visible GPS satellites, which are here labeled as Q and P. In particular, looking at the measurement model, performing integer ambiguity resolution allows us to move from like centimeters to sub-centimeter level, which is like a key requirement from this mission. But this obviously entails some specific requirements on other subsystems. For example, on the we require, in order to perform integer ambiguity resolution, we will need to have the antenna, GPS antenna pointed towards zenith to get GPS measurement from commonly visible satellites, in particular 30 degrees from zenith. And in addition, we will need to exchange raw GPS measurements in between the two CubeSats, which obviously impose a constraint on the reliability of the crosslink system, since a functioning crosslink system is indeed fundamental for the success of this type of relative navigation, high accurate relative navigation. From a control perspective, we kind of employ a unified control stack throughout all the mission modes, and as depicted on the top left. And this control stack is characterized by substantially a guidance prediction part, some kind of decision logic, which are tailored on each mode, and then some control arguments, which activate themselves in some specific modes. Moreover, we have a maneuver buffering capability, which substantially takes the optimal maneuver plans computed by our control algorithms and make substantially them compliant to the constraints which are given by propulsion. And specifically, as I mentioned, we have a combination of closed form and optimization-based algorithms, and specifically the technology demonstration on board of convex optimization-based trajectory control, we claim is a novelty for CubeSat mission. And to our knowledge, this kind of like convex optimization-based trajectory control has just been tested in flight for active control, not for translational control. So that's something unique we bring to the table, in addition of like flight testing closed form algorithms, which have some partial flight area, just for example, from the Prisma mission. Okay, I'm at 19 minutes. So I'm unsure if the presentation is 20 or 25. But I will be much faster, so no worries. I can go further. So the GNC architecture is essentially the fourth block in our. So the FDA architecture and also the safety architecture, they talk to each other, and they are kind of like the third and fourth block in our GNC. And together, substantially with the HSA FDIR, they allows us to mitigate abundant portion of the fault that may affect this mission. not all of them. So this mission remains, but actually single failure is not single failure tolerant to specific faults. Which, for example, if we lose propulsion capability on both spacecraft, we can do nothing. But we are able actually to tackle the majority of the faults that may actually affect this mission. And all the idea about this FDIR logic is that from a GNC perspective, you may receive input either from the control navigation blocks through like incapability flags, which essentially tells that either the control or the navigation are not able to function correctly. And this kind of triggers either a role switch of the spacecraft or a request to transfer back from science to standby if you're not already in standby. And if instead passive safety is violated at any time during the mission, this does trigger an escape, which is handshake with HSA FDIR. Moreover, every fault which is not GNC driven is kind of like tackled either through a role switch or through a transfer back to standby if you're not in standby. Mission is characterized by, as you can imagine, we have like several onboard models, brought from like a dynamics. I mean, we have several models of different kinds, brought from like a cinematic attitude modeling, but also, for example, here from a ballistic and dynamics modeling standpoint. And specifically, we employ on board both GBE-based numerical onboard integration of the equation of motions for mainly predictions, mean orbital prediction for absolute orbital predictions needs, which then also leads to relative orbital prediction by differencing. And then we have also the capability of directly propagating the relative motion analytically by means of STMs, which specifically are used within like the dynamics models of the optimal control problems we solve on board in real time. These models obviously contain uncertainties parameters, and here for example, we focus on 3 of them, which are actually driven, are system level driven, let's put it this way. One is, for example, the uncertainty on the knowledge of the position of the center of mass, that as we said, affect alignments. And the other one instead is the uncertainty in the knowledge of the application of maneuvers, which is obviously propulsion driven, but as you can imagine, affects the controllability of our formation flying mission. And so it's going to be interesting in the next few slides, understanding how our GNC reacts to these kind of like uncertain parameters, given the other models we are implementing on board. From a testing standpoint, we have been performing, let's say, extensive software in the loop testing, and we are moving to a phase of hardware in the loop testing. The software in the loop testing has different purposes, both mission modes. So we aim to kind of like unit test and validate the single components, and also we need to kind of like simulate in the mission in its entirety, and so simulate different mission modes in which navigation and control acts in the loop while different algorithms are working, more or less. The nominal mission scenario we are running is a 10 AM L10 sun-synchronous orbit, and the relative orbital elements of the standby and science mode are actually displayed in the table. Moreover, as mentioned, we're going to perform some sensitivity Monte Carlo analysis for understanding the performance of our system in case of uncertainties. From a navigation performance standpoint, we are achieving throughout the mission, as you can not. So this timeline, which is displayed on the x-axis, is actually a full science campaign. You can tell me if it's actually correct. So we are talking about moving from standby to science, doing 10 observations, then going back to standby. And throughout the full mission, substantially, we are able to achieve sub-centimeter level navigation accuracy with integer ambiguity resolution and sub-millimeter seconds relative velocity accuracy with integer ambiguity, thanks to integer ambiguity resolution. And these are great performances that enable then the control performance that you are going to see in the following slides. From a standby station keeping, we are actually able to. So here we have a pretty we're talking about 500 kilometers altitude sun-synchronous orbit. So you can clearly imagine how the dynamics of this formation is going to be, in particular, like on longer time horizon, is going to be dominated by the effect of differential drag. And this is kind of like clearly evident looking at the motion of the at the state space motion of the relative orbital elements in the plot on the left, in which actually Kepler couples with drag, creating this kind of like nonlinear behavior in delta lambda state component. But we are able to station keep, creating this kind of like limit salcon in the RE space. This is like actual results, station keep results over 1 week, in which we are able essentially to counteract the effect of J2 and differential drag mainly by means of this kind of like beneficial nonlinear control kind of behavior, in which we have like a limit loop that we are kind of like keeping throughout the days of station keeping, and which correspond in the relative eccentricity vector space in dead band kind of constraint satisfaction. So we are always able to keep our relative eccentricity vector contained within a specified dead band, which then waterfalls in like satisfied relative substantial radial normal separation. During transfer instead, so we need to move our standby mode ROEs down to the science mode relative orbital configuration, which entails obviously a reduction of the separation in between spacecraft, and this has to be done in a passively safe manner. And this is actually specifically achieved by keeping throughout the transfer, as you can notice looking on the plot on the right, to a synchronously parallel configuration of the relative eccentricity and inclination vector throughout the transfer. And this is, as you can notice looking at the time history on the left, these are like more or less 10 orbits transfers. So like doing 10 orbits transfers are always able to keep the relative eccentricity and inclination vector to be almost parallel, allowing for Rn separation throughout the transfer. And this then waterfalls to the profile of Rn separation, which is then directly checked by our onboard online collision detection in the plot on the left, which, as you notice, is always greater than the epsilon in phase of 3 sigma uncertainties sourced by relative navigation and even process noise, which is modeled in our covariance propagation. At any time of during these size campaigns, we are then able to safely separate our spacecraft to an escape that is modeled and tested on the right, in which substantially the escape allows to increase the tangential separation in between spacecraft, while keeping a beneficial behavior of the radial normal separation, which specifically never goes below the 20 meters in this specific scenario. The final test case, we look at the Monte Carlo performances in terms of alignment. In particular, we have checked at how the fundamental alignment requirements we're trying to achieve, so longitudinal lateral position and lateral velocity alignment requirements, how we're able to achieve them, varying the value of like specific uncertain value parameters. And specifically here, we are talking about the center of mass position error, as well as the magnitude and direction errors on maneuver application. And ultimately, what this plot shows is that maneuvers errors has actually not huge impact on alignment success. In particular, our observation success is always greater than at least 40%, even in presence of pretty large maneuver execution errors. And this can be conducted to kind of like the fact that prior to observation during science mode, the magnitude of the maneuver is actually pretty small, and the control loop is closed very fast. So we are able actually to correct pretty well and counteract for maneuver execution errors, I would say, throughout the science tracking, leading to good alignment performances. The only parameter which is kind of critical is the knowledge of the position of the center of mass, which has to be kept lower than, let's say, 1 centimeter in order to achieve the required minimum 20% success. To conclude, we have found that essentially The combination of high precision alignment requirements, close proximity, and high-risk operating environments mandate for a fully autonomous guided navigation and control architecture with unique accuracy and fault-tolerant safety performances. And we have been able to design such an architecture by means of differential GPS navigation and a blend of closed-form impulsive actuation, conform impulsive control, optimization-based control, and a safety engine, which is a combination of passive and reactive safety. And ultimately, we are able to achieve the required alignment performances, at least probabilistically, over 20%, given some specific requirements on the knowledge on the position of the center of mass. Finally, this proposed novel GNSC algorithmic architecture, while being developed for the VISORS mission, has a much more general and broader applicability, which can go through substantially any distributed space mission where high accuracy and fault-tolerant safety are key requirements. And such an application range from like rendezvous proximity operation to like satellite swarming in multiple orbit regimes. To conclude, the next step is obviously hardware in the loop, both in Stanford Space Rendezvous Lab and on the spacecraft buses displayed specifically on the left and right. And finally, we have been selected for launch in October 2024 on a SpaceX Transporter 12 launch. So we are moving fast towards like the final software delivery and launch, which is going to happen next year. Thank you.